Okay, so let me just run this program again. I've changed the data set a little bit for convenience. We have this x versus y data, and we can fit polynomials of higher and higher order in a manner that things eventually start passing through every data point. So notice that for this different data set, you still have this weird behavior as you try to make the polynomial system pass through every data point. Okay. For this data set, things are even worse. Like outside the data set, things actually go to 10 power 9 or something. Okay. In any case, and then we can plot the mean squared error. The mean squared error eventually goes to 0 if we have enough coefficients that's equal to the number of data points that you're trying to fit. You can essentially make the polynomial go through every data point, right? So you've seen that. How should we pick the optimal degree of the polynomial? One way to do that is if you actually know the amount of noise there is in your system, right? So let me just run this again. So we've plotted y as a function of x from, say, some made-up data set. And let's say you know that x was measured accurately in this data set. And then there is some noise in y, in the way the y was measured. But you obviously don't know exactly what the noise was for each data point because then you can just subtract it. But you know, let's say the standard deviation of the noise, and that this noise is unbiased. Okay. So you know the standard deviation of the noise. What can you do with that information? Okay. If you know the standard deviation of the noise, when should we stop in terms of fitting higher and higher polynomials? You can think about that for a minute. Pause the video. Okay, let's talk about that. Let me just run this thing again. So let me plot all that. Okay, and then we plot the mean square error. And then let's say the noise standard deviation is actually 0.5 here. Noise standard deviation is 0.5. What do you do with it? What you want to do with it is, so there is a difference between the model and the data. You want roughly the standard deviation of that difference to be equal to the noise standard deviation. So that makes sense, right? Making that difference between the model and the data much smaller than that means that you're basically fitting your model to noise, right? So you don't want your difference to be much smaller than the noise. So let's actually do that. And to do that, instead of plotting the mean square error, I'm going to plot the root mean square error. So I'm going to say RMSE list, or maybe I'll plot a new figure. Figure 3 is actually square root of MSE list. And these things can be the same. Let me just leave that alone like that. The root mean square error. So this is root mean square error is basically like the standard deviation, and mean squared is like the variance, right? So we're plotting the root mean square error, which you can plot like so. That's what root mean square error looks like. It also goes to 0, of course. And then let's say the noise level is known. And let's say the noise standard deviation is 0.5. What you do is just basically plot that noise standard deviation on the same plot. Let me plot that. So that's the noise level. And your root mean square error, namely the difference between the model and the data, and essentially the standard deviation of that, is higher than the noise level for linear, quadratic, cubic, and then basically equal to the noise level for fourth order polynomials, and then much smaller for fifth and higher order polynomials. So what should you pick? You want to pick that polynomial order that is basically close to, that has roughly the same amount of error as there is noise in the system, right? So in this case, at least by this metric, you want to pick fourth order polynomial as being the best possible, right? So if you're making this much lower, then it means that you're just approximating noise, which you don't want to do. Okay. So it so happens that secretly I use the third order polynomial to generate this data with noise standard deviation equals 0.5. But because it's a noisy process, you won't get exactly the right answer. But of course, if we had much more data points, thousands of data points instead of 15 data points, then this process will work pretty well, right? So you will get much closer to, I'm assuming, a third degree polynomial. Okay, so that's one method, and that's if you actually know the noise distribution in the data. If you do not know the noise distribution of the data, we might have to make some decision about where to stop based on the data itself, and we'll talk about other methods in the next video.